All right, let's get into it. We're about to embark on a kind of cosmic detective story. Our mission, if you will, is to follow the clues that have been left for us by light and gravity, all to piece together the biggest picture there is: the structure, the evolution, and maybe even the ultimate fate of our entire universe. Just look at this image. It's from the Hubble Space Telescope, a photo we call the Hubble Deep Field. Now, every single point of light you see here, you might think it's a star, but it's not. Almost every single one is an entire galaxy. Yeah, a whole galaxy. We're looking at a universe just packed with them. So you could say this is our crime scene. And the big questions are, what is all this stuff actually made of? Where is it all going? And the big one, how did it all begin? You know, every good investigation starts by just taking stock of the evidence. You have to know what you're dealing with. So our first clue is going to come from simply cataloging everything we can see out there. Let's take a cosmic inventory. So what do we see? Well, we see galaxies, lots of them, like our beautiful neighbor right here, Andromeda. These things are just massive, gravitationally bound islands of stars and gas and dust. Now, this visible matter, this is the stuff that seems to be the main component of the universe. At first glance, you might think, okay, inventory complete. But, as any good detective knows, sometimes the most important clues are about what you can't see. Well, of course not. The universe is rarely that simple, is it? The first real twist in our case comes when we ask that crucial question: is this stuff we can see really everything that's out there? The key piece of evidence is actually hiding in that graph at the bottom. It shows how fast the stars are moving as you get further from the center of Andromeda. Now, based on all the stuff we can see, the stars, the gas, you would expect the stars on the outskirts to slow way down, but they don't. Look at that curve, it just stays flat. This is a huge, huge clue. It means the stars are moving way too fast for the gravity of the visible stuff to keep them in orbit. Something else, something invisible, has to be providing a ton of extra gravitational pull. And that flat curve, it points to a truly staggering conclusion. To explain it, there must be this giant halo of unseen dark matter surrounding the galaxy. And get this, it could have 10 times more mass than all the stars and gas we can actually see. So the vast majority of matter in the universe isn't even the stuff that shines. It's invisible. Okay, so our inventory shows the universe is mostly invisible. That's clue number one, a big one. But what is all this matter? Both the stuff we see and the stuff we don't. What is it actually doing? Is it all just sitting still, or is it on the move? Well, that leads us right to clue number two. When we look at the light coming from distant galaxies, we find another critical piece of the puzzle. What you're looking at here is the spectrum of light from two different galaxies. See those bright vertical lines? Now, look at the bottom spectrum, the one from the more distant galaxy. All of those lines are shifted over towards the red end of the spectrum. This is a classic telltale sign that the galaxy is moving away from us. This phenomenon has a name, cosmological redshift, and it's not quite like a siren changing pitch as it passes you. That's the Doppler effect. This is something deeper. It's the actual fabric of space-time stretching while the light is traveling through it. And here's the crucial part. The farther away a galaxy is, the more its light gets stretched, which means the greater its redshift. Now, this doesn't mean that galaxies are just flying through space like bits of shrapnel after an explosion. A much better way to think about it is to picture dots drawn on the surface of a balloon. As you inflate the balloon, every single dot moves away from every other dot. It's not that the dots are crawling across the rubber itself is expanding. Well, space is like the balloon. It's expanding and carrying the galaxies along for the ride. So this creates a direct link, a really clear pattern. The farther away a galaxy is, the faster it appears to be moving away from us. This is our next major piece of evidence. It's a fundamental law of the cosmos called Hubble's law, and it's the unmistakable signature of an expanding universe. But wait a minute. To really prove Hubble's law, you need to be sure about how far away all these galaxies actually are. I mean, how do you even measure that? And that brings us to our third and final clue, the truly ingenious methods astronomers have come up with to measure the universe. We build something that we call the cosmic distance ladder. It's got a few rungs. For stars that are pretty close in our own cosmic neighborhood, we use a simple geometric trick called parallax. For galaxies that are a bit further out, we need something called standard candles. We use special stars called Cepheid variables that pulse at a rate that's directly tied to how bright they truly are, so we can calculate their distance. And for the really, really distant galaxies, we need the brightest things we can find, Type A supernova. These incredible stellar explosions are like cosmic lighthouses, shining with a predictable brightness across billions of light years. Each step on the ladder helps us calibrate the next one, letting us measure the true vastness of space. So, there we have it. We've got our clues. The universe has a ton of unseen matter, it's expanding everywhere, and we have a way to measure it all. Now it's time to put it all together. This case is about to be cracked wide open. And here it is. This is the smoking gun. When you plot the velocity of galaxies, which we get from their redshift, against their distance, which we get from our cosmic ladder, you get this beautiful, unmistakable straight line. This is Hubble's law staring us right in the face. It's the triumphant confirmation that we do, in fact, live in an expanding universe. Now, when we map the universe on the very largest scales, another profound property just pops out. No matter which direction you look, the universe appears, statistically speaking, the same. There's no special direction, no center, no edge. This fundamental principle is called isotropy. And you can see this isotropy most perfectly in this map. This is the cosmic microwave background. It's the oldest light in the universe, literally the leftover heat from the Big Bang itself. And it is astonishingly uniform. The temperature is almost exactly 2.728 Kelvin everywhere we look. This tells us that the early universe must have been incredibly smooth and simple. But that word almost is the key. Because if you crank up the contrast on that map, you see these tiny, tiny temperature fluctuations. We're talking differences of mere millions of a degree. But these little spots, they are the primordial seeds of everything. Over billions of years, gravity got to work on these slightly denser regions, pulling in more and more matter, and eventually forming all the stars, all the galaxies, and all the clusters we see today. From this faint, ancient echo, everything we know arose. So our cosmic investigation has led us to a complete inventory. The universe is made of the galaxies we see, yes, but also the faint radiation left over from the Big Bang, a huge amount of mysterious dark matter holding everything together, and something else called vacuum energy, or dark energy, which is actually causing the expansion of the universe to speed up. So we've followed the clues, we've traced the great expansion all the way back to a hot, dense beginning, and we've inventoried everything that's in the cosmos. But, just like any great detective story, solving one case only reveals an even deeper, more profound mystery. We know dark matter is there. We can see its effects everywhere. But what is it? What is this stuff that makes up most of our universe? The investigation, as they say, continues.